is going to be okay. Okay, so I'm going to kind of give an overview of some work I'm doing on maybe a little bit of a different approach to microwave remote sensing. That's using signals of opportunity. I know after this there's going to be 2 talks on GNSSR, so I've kind of minimized the amount of GNSSR discussion I have in my talk. Again, I'm Jim Garrison. I'm at Purdue University, just a short 5-hour drive from here. And I start my talk with kind of stating the problem that I'm hoping to solve with signals of opportunity. And as many engineering problems go, you sometimes come with this idea for the solution first, and then you go back and find the problem. So it maybe kind of follow that approach, but I'm going to present this as a problem, and then this work as a solution. So the problem I'm going to present is all of our measurements, all of microwave remote sensing has to take place in frequencies that fall within a kind of narrow range of the electromagnetic spectrum. Because there's only a small window that the Earth's atmosphere is mostly transparent to microwave frequencies. And we like to use that because we can put satellites in orbit and see the Earth without much of a problem. Radio astronomers like that because they can put instruments on the surface of the Earth and see things external to the Earth without much of a problem. But also communications companies like it because they can transmit all kinds of signals and use a bandwidth to provide services from satellites. So educating all these different users and balancing all of them is just the job of the spectrum allocation world. And so these narrow range of frequencies that penetrate the Earth's atmosphere are what I call very valuable real estate. And only a small amount of this is allocated to science and protected for science. Navigation and communications occupy a much larger part of the spectrum. And in dealing with, even if you have a license on a certain band, the power of these communications transmissions, either from satellites to the ground or on the surface of the Earth, is so much stronger than the types of measurements that we are measuring for science. So even if we are within a protected band, it's probably not going to be clean. There's going to be stuff leaking through. Okay. So the idea of signals of opportunity is, well, why don't we just use some of these signals that already exist? Some of these powerful communications transmissions are basically sources for a bistatic radar. And this is a little animation I made up, or one of my students made up a few years ago that shows, okay, we have a communication satellite here. If that was a radar, we have this very small amount of radar backscatter, and that would be the measurements that Kamal was talking about. But in the forward scatter direction, we have much stronger signal. And then if we can also see the direct line of sight, we have these kind of 2 sources. And so that's kind of going to replace the idea of our transmitted signal and our reflected signal in a conventional radar. It'll be the direct signal we see along the line of sight, the communication satellite, and the scattered signal. Okay, and I've been involved in this basically for most of my postdoctoral professional life. I did the first measurements of GNSS reflectometry right after I got my PhD when I was working for NASA, and these are kind of the first measurements, and this, not good, but first demonstration of the measurements was a scatter plot of ocean wind speeds using reflections of GPS signals. And again, there's going to be 2 talks after this about GNSS reflectometry, so I'm just going to quickly kind of say where all this went. This is the animation for Cygnus. This is the published results. So that technique of measuring ocean winds from distortions in the correlation function of GNSS signals has evolved and is now on a mission. But I want to ask a question, and that is why, of all of these signals that are being transmitted, all these existing sources, why was GNSS the one that we chose to look at 20 years ago? Well, obviously, it does provide illumination of the entire Earth by design. The constellation's designed so at least 4 satellites are visible with some statistical occurrence, like 99% of the time, anywhere on the surface of the Earth. To solve the navigation problem, you need 4 equations to solve for the 4 unknowns, your position and a clock bias between the receiver and the transmitter. L-band is a good frequency because it penetrates atmosphere vegetation pretty well. Again, that was designed for the navigation use. You want to be able to navigate in all weather conditions, but nobody really intended to navigate underground. So it doesn't penetrate the soil very well. It's too high of a frequency to penetrate too deep into the soil. But the key point that I'm going to talk about is that the navigation solution uses a pseudo-random noise code, a PRN code. So these are not communication satellites, and I do a whole section in my graduate course on signal processing in GNSS to show the difference in what properties you want to design the modulation for communications versus design the modulation for navigation. They're designed for ranging. They transmit a known, repeatable pseudo-random noise code. As far as a data transmission, it's a very low rate data message, 50 bits per second. That's all the new data that's being transmitted by the satellite. So it uses the pseudo noise code designed for ranging and designed for mapping and delaying Doppler. That's key to how it works. And then also, of course, my career began with GNSS. My PhD had nothing to do with remote sensing. It was all on GNSS navigation. So I kind of brought my perspective into this, not from coming from a remote sensing graduate program. Okay, but what about other signals? And about 10 years ago, I started looking at what else could we use, and some of this was brought on just by the availability of commercial systems that allows in software-defined radio to really do some very flexible signal processing without having to have the expertise for building microwave hardware from scratch. So that the availability of these systems commercially was one of the things that kind of brought some of this about. There's approximately 400 communication satellites operating in GEO. They have a number of different bands. There's a lot of transmitters out there, a number of different beams to different sections of the Earth. So it's not uniformly distributed, but there's a large number of satellites out there. The design of communication signals is different than navigation. Communications, in order to get a sufficiently low bit error rate to close the link budget, you need very high power. So communications transmitters are typically about 30 dB stronger EIRP than navigation signals. Pretty much any band you're allowed to transmit on, because it's very valuable real estate, somebody's going to be transmitting on that band. There's not any empty lots in very desirable neighborhoods for too long. Someone's going to occupy that band. But the problem is that they don't have the pseudo noise code. They're designed for communications, not ranging. So we made this assumption that, well, if there's good encryption and good compression, they're basically turning what they're transmit into a noise-like signal. So we did some early experiments with just looking at some existing communication satellites. We bought some DirecTV dishes on eBay. We got like 20 of them for at some eBay sale. We started making these measurements, and we started saying, well, cool. We generate an ambiguity function from these communication signals, and this was one of our first ambiguity functions we generated. This is for the transmitter for DirecTV. One of the channels on DirecTV, I think, is 25 megahertz wide. So that's compared to what we're used to with GNSS, that's a pretty narrow ambiguity function. And so that gave us confidence we can process these signals the same way we process the GNSSR signals. So one of our first experiments, and it was kind of the frequencies we selected were kind of mostly based on the signals that we knew existed that had simple enough signal structures that we could analytically model that ambiguity function, and that we could buy the hardware commercially made. So it turns out those first experiments were at KU band for DirecTV. It turns out the XM radio signal is one of the most powerful communications transmitters that's out there. It's S-band. It's about 2.3 gigahertz, and we could get antennas made with both polarizations that are aircraft certified. And we built this system, and we got free flights one season on the NOAA Hurricane Hunter. This is no bigger than like a GPS antenna. We have one of these on the top of the aircraft, one at the bottom. We basically just used a software-defined radio, recorded the wideband signal, and then we did the same processing we did with GNSS, where we have a model for the scattering for the delayed Doppler map and the forward scatter, and then we fit that to the measured delayed Doppler map. And so we, over a decent range of wind speeds up to like 40 meters per second, we looked at retrieving wind speed. First of all, we used a subset of this data to calibrate our model function, because we want a relationship between the slope distributions, as we talked about earlier, and the wind speed. And there's one model is developed for L-band. And so we developed our own model. It's a slight change from the L-band. And we're able to do these retrievals. We tuned the model on SFMR, which is an airborne radiometer on the NOAA aircraft, on a subset of that data. And then we checked it against 3 other validation sources: the SFMR, HWRF, which is a model, GPS dropsondes, which are released from the aircraft, and then the aircraft flight level winds from the avionics system, projected down to the surface of the Earth. So we showed we could do these retrievals. That's kind of a demonstration. But really, what types of things could we do with this that would have a real utility in Earth's remote sensing? And what types of geophysical measurements can we make that are not currently made with existing systems? So we started to look into this a little further and thinking along those lines, and going back to the idea that we can now operate anywhere in the spectrum that somebody's transmitting, and we have these signals for free. So it's kind of 2 directions my research is going since then. The first is at very low frequencies, or for microwaves, very low frequencies, P-band. And why P-band is useful is because of penetration through vegetation and penetration of the soil. But I'll show why that P-band has not been used much in remote sensing for, again, the issues of radio frequency interference because of the use of other transmitters on that band, and also in radiometry, the size of the antenna becomes very, very large. On the other end of the spectrum, going back to the higher frequencies, one of the things about these high frequency transmitters like KU and Ka band, there's a very large bandwidth that's owned by some of the communications users. The satellite we've used for DirecTV is a 500 megahertz bandwidth. There are commercial communications satellites that have a gigahertz of bandwidth that's licensed to them, and there's some Department of Defense satellites also have about a gigahertz of bandwidth. So that's a gigahertz of bandwidth for free. So I think in one of our proposals, the current market value of a gigahertz of bandwidth is a few tens of billions of dollars. Okay, so why going to the P-band? This just shows a simple plot of penetration depth. This is not any type of sophisticated layered model. It's just the complex term of the dielectric constant. And then we show as we go from L-band here, if there's a reasonable amount of soil moisture, you get a few centimeters of penetration. If you go down to the P-band, and these are 2 of the bands for the satellite that we're looking at. One is from 230 to 270 megahertz, and the other one's from 360 to 380 megahertz. There's also satellite communications transmitters all the way down to I-band at 137 megahertz that we're looking at as well. And so you see the penetration depth could go down to 20 to 30 centimeters. And it's getting us down to making direct measurements of root zone soil moisture, which is currently not available except as a data assimilation product. And again, I mentioned why P-band hasn't been used that much. These show some earlier studies of P-band systems at 435 megahertz and 137 megahertz. You'll get large antennas. The ESA biomass mission, which is to look at penetrating through dense biomass. That's also in the 437 megahertz. But not only are these antennas large, because of the issues of competing for spectrum, currently ESA biomasses can't operate in North America or Europe because of a spectrum allocation for space tracking radar. Okay, so with those ideas, we wrote a proposal in 2013 to the Instrument Incubator Program, which is to develop prototype instruments. And we proposed an airborne demonstration instrument at P-band, and we also included S-band kind of just to show, since we had a heritage of experiments with S-band, we included that as kind of to show that we can do similar processing of both bands. And as an airborne instrument, again, technology demonstration. This shows it on the NASA Langley Research Center aircraft. Because these satellite transmitters are geostationary orbit, we used a two-element antenna that NASA Goddard built, looking out the side of the aircraft, and then we flew in an east-west direction, approximately perpendicular to the direction of the geostationary satellite. And so we'll collect data on half of our flight, and then we won't collect data on the return flight. And so we flew like this lawnmower pattern over the Little Washita watershed in Oklahoma, which has a lot of instrumentation there for soil moisture measurements. We also flew with SLAP, which is the airborne prototype for SMAP. It has active and passive S-band and L-band. And so we have simultaneous data from those two instruments. Okay, so unfortunately, the week we flew, there wasn't any rain, so we basically have two values. We have the dry soil, and then we have our calibration targets that we flew over these lakes. So we're in the process of submitting a paper to TGARS on this. So we're not, since we only have 2 points, we can basically just look at the statistics of our reflectivity retrieval, but we did do some work as far as like a vicarious calibration of the antenna pattern over the water, because that turned out to be one of our problems. The other interesting thing is flying over these rivers and small lakes is we got an assessment of the resolution. Our assumption is all of this is in the specular range, coherent scattering. So our resolution is set just by the Fresnel zone of the about meter wavelength. So we have some evidence that we're to calibrate what our resolution is. One of our points that we were saying with the use of signals opportunity is our robustness to or our ability to use bands that are not allocated to science and not protected for science. So inherently thought, well, that would give us some robustness to RFI. We did see 2 examples during this week that we saw extremely high signal powers at some points. And we suspect that may have been a type of RFI. So during this aircraft experiment, those are the only examples. Now, since that time, since the IIP was just a technology demonstration, we wanted to also look at developing some algorithms and looking at some of the science. So we put together this field experiment with this portable tower. And these antennas are not commercially available for these frequencies. So we tried our hand at building our own antennas. These are just simple dipoles with a large ground plane. So it's a linearly polarized antenna. The transmitted signals are circularly polarized. And have this is one of the agricultural research fields at Purdue. So it's well documented, like the soil types and the soil structure. And we installed, in 2017, we installed soil moisture probes in between 2 of the drainage tiles at 4 depths. And then we set the tower up so that the specular points would, in our plan, lie between these 2 drainage tiles. So it will be maybe kind of more of a uniform soil moisture. This shows the one Fresnel zone for the S-band XM radio, and that's for the other S-band satellite. And then this one, you see it's drifting. That's one of the XM radio satellites that's being decommissioned. Now, our source for these P-band measurements is a Department of Defense communication satellite. The orbits, are publicly available. It's geosynchronous. It's not geostationary because there's a small inclination. So, in looking at the orbits, we see that, the satellite position does drift a little bit. Okay, so we do definitely see a large diurnal variation due to this drift. Both due to the drift because of the, the angle of incidence changes. Also, we're going back and forth over these these drainage tiles that are in the field. So in the 2018 experiment, we went back to the site. We were a little more careful about the geometry. We installed more soil moisture sites. We have a set of probes that's right over top of the drainage tiles. And then we're also, in 2018, we also went through a year, a whole season of the corn growth. And so we took the biophysical measurements of the corn by looking at the vegetation water content and the structure of the corn plants. We went through we followed the protocols on that to get a good measurement of the effect of vegetation. And so we're still processing this data. I should say we are seeing some evidence of RFI in this data. Right next to that band, there is another band that's allocated for like emergency services and stuff like that. So some of those, we recorded quite a wide bandwidth during these experiments, so we can see what's outside of the band we're interested in. So there is, there's a lot of other stuff in that band. So we're still working on processing the data. Okay, back to the higher frequency measurements, wideband. There, the event, there we're looking at altimetry. And some of you may have followed GNSSR, know that one of the first measurements proposed for GNSSR was actually altimetry, ocean altimetry. And one of there's basically two problems with GNSSR for altimetry. One is that the transmitted power is very weak, and also the bandwidth is small. And so maybe I'm actually thinking I'm going to skip ahead to apply and then go back to this one. If we look at a simple air model for the range tracking of a altimeter waveform, we'll see it depends on two things: the signal noise ratio and the bandwidth of the signal. But once the signal noise ratio is sufficiently high enough, we see it pretty much only depends on bandwidth. Okay, basically, inversely proportional to bandwidth. So wider bandwidth, better tracking error. Okay, if we're low SNR, then we're down in this range. Okay, so the open signals for GNSS for the GPS CA code is about 1 megahertz of bandwidth. Galileo, the European system, has a channel that has a total of about 80 megahertz of bandwidth. Remember, for these direct TV signals, for the communication satellites, we're talking 500 megahertz to a gigahertz of bandwidth. Okay, so with that idea in mind, the model predicts that we can get altimetric precision of a few centimeters, or about 1 or 2 centimeters, which is comparable to what active radar altimeters get. But the difference is that since we're passive, we don't need this large radar. We could launch a constellation of small satellites for much less than the cost of something like SWAT. So we did some. One of my former students, who's now at JPL, did these simulations looking at this eddy event in the Monterey Bay, the coverage with a single altimeter in a 10-day repeat orbit. We only get it's 10-day repeat, so we only get these tracks for 1 day, and then we simulate that with an 8-satellite signals of opportunity constellation, seeing all of the transmitters that are in view, and so we get a much denser sampling with the signals of opportunity. This is so we did some field experiments to look at really can we track these wideband signals. One of the things that's a little bit different than the previous experiments is this is not a single channel. This is a band that's allocated and it's got like 20 individual channels. Okay, but again, our assumption is even if they're all driven by different clocks, it's just band limited noise. So we don't need to individually demodulate any of those channels. So can we just process this whole thing as a single wideband signal, using the techniques of something like VLBI. So this shows an example of the spectrum from XM radio, from direct TV, and then you see the individual channels. We built a experiment at the Harvest platform, which is a JPL CalVal site, again, using our commercial antennas. One of the things in using these commercial antennas is that they down convert the signal at the feed horn So each of them has its own little oscillator. So there's a frequency drift between the two of them. So we use a beacon that is this little tiny antenna that's basically transmits into both of them, and then we calibrate the time and frequency offset using the beacon. So we did one experiment in 2014, 2015, where we just looked at tracking a single channel. And then we got this wideband system that basically is designed for radio astronomy. We made some modifications to it in order to basically to add this beacon, so we can get the time and frequency offset. We did a 3-day experiment over so we can at least see the change in the tidal cycle, 400 megahertz. We recorded the wideband signals in post-process, so we had quite a bit of data coming back. And so then we tracked the reflected signal, estimated an altimeter height, and then compared that to our model that we had before. Now, again, this is only at about 25 meters above the ocean surface, but we were comparing our measured altimetric error to a model, which was the purpose of this experiment. So we got a few centimeters error. And I show these because this is averaged over 1 second. One of the issues in getting the alignment of the errors that we were retrieving versus the model was the fact that the tide gauge and the LiDAR were not perfectly synchronized with our measurement. So we then also went back and looked at only taking that 5 millisecond shot of data that was closest to when the LiDAR measurement was made. And so, of course, then the error bounds get larger, but we saw a smaller bias between that and the LiDAR because just within the averaging time, the sea surface height is changing a little bit. Okay, so with this these basic research activities, we're now looking at some mission design concepts. This is just a little simulation we put together. So the idea is changing, instead of looking at scanning antennas or anything like that, since these looking at constellation of small satellites, and we can build up Earth coverage by just combining the measurements, just to show some very simplistic simulation of a transmitter, a GEO, and I think this is 8 satellites in a constellation. And we've recently, or a year ago, were awarded a NASA CubeSat mission called SNOOPI, Signals of Opportunity P-band Investigation, which builds on our instrument incubator, and we're going to look at validating some key parts of the technology related to the P-band measurement for root zone soil moisture, and then also a related measurement that JPL is working on is snow water equivalent, where you can look at the phase change through penetrating through the snow layer. Okay, and again, this was a technology demonstration, and one of the questions we were asked after the IIP ended, and we give our final report, what needs to be done for the technology development. I mean, we have a lot to do with the science, but what needs to be done with the technology development? Because these low frequencies is nothing, as far as the hardware design, that's really challenging. But we came up with 3 things that could only be demonstrated in space as justification for the SNOOPI mission. The first is that, we are assuming all of these measurements are coherent. We don't know the effects of different types of terrain, different types of vegetation. So that's really essential to making these measurements work. So it's, all of our simulations assume that we have a coherent signal. So over a sufficiently large set of test conditions, we want to look at the statistics of the phase of this scatter signal from orbit. The other thing is, we're basing the ability to make these measurements on the fact that, we're going to have more robustness to RFI than a radiometer or a radar in P-band, and that's based on these ground-based experiments, these airborne experiments, and the basic assumption that we're not trying to pull a very weak signal out of noise. We're dealing with measurements of this very powerful communication signal, but we don't know what that looks like in space, where we have wide beam antennas that are seeing large sections of the Earth's surface, and this powerful signal is just one part within that beam. So I think that's going to be a big thing that we're going to try to determine with this mission. And then lastly, there are some technology development issues, even though these frequencies are not that challenging from a RF standpoint for designing the hardware. One of the biggest challenges is that we don't control these sources. So we have to have algorithms in our receivers that are robust enough to pull these signals that we don't maybe have an accurate orbit knowledge of. We don't have an accurate understanding of the spectrum at the instant that we're making their measurements, because they do change the power, they do change the modulation. So the third point is just an engineering demonstration that the receiver design can work with quite a bit of uncertainty in the source location and the signal structure. So this shows our current iteration on SNOOPI. We're just using communications antennas. These are wide beam cross dipole antennas, commercially available at the two frequencies, the 255 and the 370 megahertz. Notice we don't have a direct and reflected antenna, because we'll get to how we're going to process that data. The Science Operations Center is set up at Purdue, where we look at the first data that comes back. And now that because one of the challenges with these very low frequencies putting on a CubeSat is we couldn't get good isolation between the direct and the reflected signal. But they do have a long time delay. So we're going to process an autocorrelation of a single channel. And I worked through the math of this, and we have some simulations I'm going to present next that show that we can look at the autocorrelation or track the direct, we'll track the autocorrelation zero delay, which will be both the direct and the reflected added together. And then we see the autocorrelation at the reflection point, which would be basically related to the ratio of those two. And so we drive the statistical model. There is a loss in SNR in doing that versus two perfectly isolated antennas. And this shows for a single shot observation at, I believe, a 1 millisecond integration time. And so we see quite a bit of an increase in the error, but we can incoherently average over a second to reduce the error down, and also average over all of the channels. One of the bands has 4 channels that are always on as a wideband CDMA type structure, and then the other channel has the other band has maybe about 10 channels, but they're dynamically allocated. They turn on sometimes and turn off other times, and they're very narrow band. They're like 25 kilohertz. Okay, I'm not sure how we doing on time.
You're done.
I'm done. Okay, all right. Sorry. So I'll just get to the conclusions. Sorry, you should have waved at me. Okay, so conclusions. Signals opportunity. ProSense is a third way of microwave remote sensing. Smaller, low power instruments. The design of the receivers are going to have more of a basis from history of navigation and communication architectures. And the big thing is that we can make measurements in communications and navigation bands. The challenge is that we don't have any control of the signal source. So whatever receiver we design, signal processing, we have to be robust to changes in the signal structure. And the bistatic geometry is a lot more complex. So the calibration is going to have a lot more variables, more complex geometry. Okay, thank you very much.